All right, in this last piece here of 5.6, we look at a global overall strategy for looking at series in general. So we had to go back and remember we looked at harmonic series, we looked at p-series, we looked at geometric series, we looked at alternating series, we looked at the comparison test, the limit comparison test, the divergence theorem, and we looked at the root test and the ratio test. So all of these different tests and these different ways to look at series, we're going to bring all together to formulate a strategy. So the first thing when you're looking at series, does it look familiar? Is it a harmonic series? We know that diverges. Or is it a harmonic series combined with alternating sign? We know that that one converges. Also, is it a p-series? We know that p-series converge for p bigger than 1. Is it a geometric series? We know those converge for the ratio r, the absolute value of that less than 1. So are there series that you're given that look like something you've seen before? Okay, so that's the first strategy. Is it something that you already know about? The second thing is, well, if it's an alternating series, all you need to do is show that the a sub n's tend to 0 as n goes to infinity. So if that's the case, then the alternating series converges. Now, do you want absolute convergence or do you just want conditional convergence? The alternating series test tells you about it converging, but if you want to know if it absolutely converges, you're going to need something like the ratio test or the root test. Okay, so be careful when you have alternating series and look at the question. Is it asking for convergence that's conditional or absolute convergence? If you see a series that's similar to a p-series or geometric series, maybe you want to do a comparison test or a limit comparison test. Okay. Do you see factorials inside of the a sub n's? Then maybe you want to use the ratio test. If you see powers of n, then maybe you want to use the root test. And finally, you always have at your disposal the divergence test and the integral test. Remember, the divergence test, if the terms don't go to 0, then of course the series diverges. Now, the divergence test can't be used to show convergence. It can only be used to show divergence. We also have the integral test. That was one of the ones we had in the early sections of Chapter 5. If you can bound your terms of your series to be less than some f of x whose integral converges, then you can use the integral test as well. All right, so we've got all these different tests at our disposal. This is a nice strategy. Does it look like something familiar? Is it an alternating series? Can I use the alternating series test? Does it look like a p-series or geometric series? Maybe I need to do a comparison test or a limit comparison test. Is there a factorial in the series? Then maybe I could use the ratio test. Are there powers of n in the terms of a sub n? Then maybe I could use the root test, etc. So we're going to bring everything together to come up with a strategy. Let's look at some of these. I'm not going to go through the details. The textbook, if you look in the end of section 5.6, we'll go through the actual details. But I just want to give an overview of how to look at these things. Here's one example. Notice the degree in the numerator is 2, the degree in the denominator is 3. So as n gets large, this looks like 1 over n. I would do a comparison or limit comparison test with 1 over n. And 1 over n is a harmonic series which diverges. So you'll find that this diverges. Okay. Over here, the next series, it's alternating series because of the minus 1 to the power here. And I have a 3n plus 1 and an n factorial. So here, if you just look at wanting to see if this thing converges. There's the alternating part. That's a minus 1 to a power of n here. Now, to show that the alternating series converges, I just need to know that this goes to 0. Well, 3n plus 1, so that's the power of n, divided by n factorial. Remember, n factorial is n times n minus 1 times n minus 2, etc. So the first term in the n factorial divides with the 3n plus 1. This will look like a 3 for the first term, and then I still have an n minus 1, an n minus 2, an n minus 3, etc. in the denominator. So this will clearly go to 0 as n goes to infinity, and so by the alternating series test, this series converges. But we can also say more. If we look at the absolute value and apply the ratio test, or if we look at the absolute value and applied a limit comparison test, now I would go ahead and use the ratio test. It's pretty easy to show that this thing converges absolutely. All right, so here, first of all, it does converge by the alternating series test, but I would go ahead and employ the ratio test to ensure that this thing converges absolutely. The next one here, I've got e to the n over n cubed. So here, e is just some number between 2 and 3. So think about this as worst case scenario, 3 to the n, and this is n cubed. Now, I'm going to just think about this. This numerator is getting large very fast, and the denominator only gets large with the cube of n. So I'm guessing that this might not converge. In fact, if we look at the limit as n goes to infinity, this looks like infinity over infinity. Using L'Hopital's rule, I'm going to get e to the n over 3n squared, but that also is infinity over infinity. Using L'Hopital's rule again, I'm going to get e to the n over 6n. Again, that looks like infinity over infinity. Using L'Hopital's rule for the third time, I'm going to get e to the n over 6, and as n goes to infinity, that goes to infinity. So this is going to diverge by the divergence theorem because the terms in this series don't even go to 0. So here we used just one of the very first theorems we learned in chapter 5. Looking at this last example here, notice there's a power of n and a power of n in both the denominator and numerator. I would quickly employ the root test, which we just looked at in the previous video. And when you apply the root test, I'm looking at the limit of 3 over n plus 1 as n goes to infinity. That clearly goes to 0, and so by the root test, this would converge absolutely. So we have all the different strategies here that we can at least pick a strategy to employ on a particular series. If that doesn't work, pick a different strategy. But these steps 1 through 5 give a nice flow in what to choose for a test when you encounter a random series. All right, that concludes chapter 5.